Hi. So just to say that both Flere, who gave a talk this Monday, and me, who has a poster, are speakers at a summer school this August in Antwerp on local global principles and quadratic forms, and there's a lot of valuation theory there. So if any of you or PhD or master students are interested, then well, look up the title on the internet or ask me. Yeah, thanks.
Okay, so for the last talk of this morning, we welcome Sebastian Krapp, who is going to tell us about definable, convex, and henselian valuations on ordered fields.
Yeah, thank you very much, and also many thanks to the organizers for organizing this wonderful conference and giving me the opportunity to speak here about some topics in, let's say, valuation theory of ordered fields. Before I start, also on the billboard up there is this homepage, which I bought and pay €6 a year for in order for you to get my handout, because I think that when you have the slides, sometimes it goes a bit fast, and so anybody who has some kind of device can download it now after the talk at any time. Okay, so I'm going to report on joint work with several people. I realized in the preparation that maybe I was, not thinking enough that 4 papers can't fit into one talk, but I'm trying my best to give kind of a collection of nice results from these 4 papers. So I'll mainly concentrate on the first 2, which are joint works with Salma, no, not the first 2, it's the last 2, sorry, in this order, which are joint works with Salma Kuhlmann and Moritz Link on the one hand, and the other paper is joint work with Philipp Dittmann, Franziska Janke, and Salma Kuhlmann. And if time permits, I'll also talk a bit about kind of where the work started in the first 2 papers. Okay, so yeah, one thing, I mean, maybe me also speak for some of the junior researchers here. One thing that is kind of overwhelming here is that I'm going to present many things where there are at least, for every slide, 10 people in this room who know much more about it than me. So I was trying, so what could I do? And what I'm trying to do is to give you my motivation. So I come from order theory, and I'm trying to give maybe not the historically correct motivation behind everything we do, but kind of my personal motivation, how I kind of dived into this topic. So the main part of the talk is going to be about henselian valuations and convex valuations. And then this is kind of the minefield for me. If I do not talk too long about the first 2 topics, then I also talk about almost really closed fields in connection to the study of NIP fields. Okay, so let's get started. So also as a warm-up, let's fix the language that we have, the model theoretic setting that we have. So there's a lot of binary things going on here. There's henselian valuations, there's convex valuations, there are 2 languages, that's very important. So a lot of results are comparisons between definability in one language compared to another richer language. And the 2 languages are the language of rings and the language of ordered rings. And in order to not get confused, I really try to make sure that all ordered fields, which are considered in the language of ordered rings, are denoted by K, and all fields which are possibly real, but also possibly any field without any linear ordering, denoted by F, and G always denotes an ordered abelian group. And the other thing that you always have to mention at the start is that definability is definability with parameters. And I specifically say when we have definability without parameters, zero definability. So that's kind of the other binary thing going on here. So we have also the notions of definability with and without parameters. Okay, so let's also set up the valuation theory. So the first thing I have to mention is we have a valuation V and the value groups denoted by VF, and it is an additive ordered abelian group. And I use standard notation for the valuation ring of elements with non-negative valuation and of the valuation ideal of elements with positive valuation. And the residue field is denoted by FV. I really hope that I didn't mix it up because it's kind of a confusing notation when you write it down. And residue elements are always denoted by this bar, but they will not come up that often. Okay, so here's my personal motivation that I maybe started with pretty much 5 years ago when the last conference on these topics were held here in January 2018, I think it was. So the question there that interested me was, is the language LOR more expressive than the language LR? And you have to fix the setting. It's always in the context of ordered fields. So what does that mean? So it means that you can always look at sets which are definable. And the, very basic question that probably many people could think of many examples now is, are there definable sets in the language LOR which are not definable in the language LR? Okay, so that is kind of my interpretation of expressive power of a language. And you would expect, and the expectations are right, that of course if you have a richer language then you should be able to express more things. But let's look at some examples, the examples where I was coming from. So if the ordering is already LR definable, it's a very basic observation, then the answer is obviously no, because you can define everything in the new richer language in terms of the old language, as long as everything in the richer language is definable in the old language. And this is not some example that never comes up. It comes up in many cases. So O-minimality. When we are real closed, then we can define the set, the positive cone, the set of in this case, the set of positive elements by this LR formula, expressing that the positive elements are the squares of non-zero elements. And more generally, we can look at ordered fields where every positive element, every non-negative element, I should say, is the sum of n squares for fixed n. So then, once the n is fixed, we can express also p less than with one single LR formula. And this is, for example, one certain class of these fields which are not O-minimal are the Euclidean fields. So, for example, Euclidean fields are those fields which, let me give you an example. The smallest Euclidean field would be just taking the rational numbers and then closing it under square roots for positive elements. So that would be an Euclidean field. Okay, so I gave you some fields where the answer is no, but generally, yes, the language of ordered rings is richer. And to come up with an example, actually, I think it's not too easy. I gave you one quite interesting example, because I think in many cases where I try to find examples of, let's say, non-definable sets, I really always used this field here. And it will come up later in a certain results about definable valuations. It is the rationals, and then it join countably infinitely many transcendental elements. And in order to talk about this in an ordered context, we can choose a particular ordering. It doesn't really matter which ordering we choose. So I just choose the one where each of the transcendental elements is infinitely larger than the previous one, and all of them are infinitely larger than any element in the rationals. And the interesting thing about this is these are extremely many degrees of freedom. And so you can apply very first model theoretic first year course principles to show that the ordering here is not definable. Because whenever you have a formula phi, so here I have these y1 up to ym to stand for the parameters that I can plug in, and x1 and x2 to be, the free variables which stand for, where I can plug in the elements I want to compare by the ordering. And the thing is, no matter what parameters I choose, for simplicity, without loss of generality, I chose t1 up to tm because whenever you have parameters in this field, then actually you can choose them among here, because in model theoretic terms, the whole field is just the definable closure of the set of the ti's. And no matter how many parameters I have, the next two elements cannot be distinguished. So I can find an automorphism fixing t1 up to tm, an LR automorphism, but just exchanging these two elements, which is fine because these are all transcendental. And then this tells me that this formula holds in K if and only if this holds in K. And that means that this formula cannot express that tm plus 1 is less than tm plus 2, because it would believe in both directions. Okay, so I think it's a very nice example. And as I said, it will come up later also in the definability of convex valuations context. Okay, so convex valuations. I think convex valuations in the context of ordered fields are, the nicest one to consider, the most natural ones to consider. A valuation is convex if its corresponding valuation ring is convex. And many people, I mean, sometimes I get asked, what does convexity mean? So whenever I talk about these notions, I mean with respect to the given linear ordering. So convexity of the valuation ring means that whenever I have two elements in the valuation ring and an element in the field lying between them, then this element in between must also be in the valuation ring. But there's also another reason why I think they are quite nice. So if I have an ordered field K, then a convex valuation ring, it has to contain 0, it has to contain 1. And it has to be a ring. And it has to be convex. So a convex valuation ring always looks like this. So any ring which is convex, containing 0 and 1, is a convex valuation ring, because the valuation ring property that any element of K or its inverse, any non-zero element of K or its inverse lies in OV, is naturally satisfied just by the ordering that we have. And so one thing you immediately see is that the set of convex valuation rings is linearly ordered by inclusion. So coarsening is just a linear ordering on the set of convex valuations. And that kind of makes the setting much, much easier, because in general valuation theory, you have all these pictures of brooms and things that go in many different directions. In the convex case, everything is nice and comparable. And what we also have is we can switch to the residue field and still have the ordering. So whenever we have a convex valuation, then the residue field really directly inherits an ordering from upstairs, from the big field. I mean, the residue field is just cut off the infinite elements, for example, and then identify everything in here which is infinitesimally close to each other. These are convex equivalence classes, so you have an ordering on the residue field. And to me, the most amazing result back then was the one that connects Henselian and convex valuations. So there's this, maybe a bit underappreciated result of Knebel and Wright from the 1970s that says that any Henselian valuation on any field is convex with respect to any linear ordering, making it an ordered field, on that field. So any Henselian valuation is convex with respect to any ordering. So in that picture, you could imagine that once you have a Henselian ordering, it will appear at some point. Maybe this one is not Henselian yet, but maybe the next coarser one is Henselian. So, and then from then on, you also know that Henselianity is preserved by taking coarsenings. So what you have here is you have a few convex valuation rings. Then at some point you might stumble across a Henselian one, and from then on everything bigger is still Henselian. So you have all these nice properties in the study of the class of convex and Henselian valuations on a given ordered field. Okay, and the most important field in the study of Henselian valuations, of course, is the field of generalized power series. I just want to briefly introduce the notation I use. So I use the notation with a double bracket and then just a group inside. And the elements, they might come up once or twice, are denoted as these formal sums. And the valuation, which I denote by V min, just is the, I have to choose my words carefully, is the standard valuation on the field of generalized power series, just finding out from a particular power series which one is the first non-zero coefficient, and then just take the power of that monomial, and that's the valuation. Okay, and also, to me, these fields are particularly interesting in the ordered context. So whenever you have an ordering on the residue field, so it's kind of now going in the other direction, you also get an ordering on the big field, on the field of power series, by, again, looking at the monomial with, the least monomial with non-zero coefficient, and if that is positive, then the whole element will be positive. So that's the standard ordering that you get from going from the residue field, in this case big K, to the power series field. And one very interesting result also, which is exploited in, I guess, every single work I'm presenting today, is the aix-marseille principle, but in the extended language, the expanded language. So we also have the aix-marseille principle. This is just one of the cases. So the results of Farey in 1993 were much broader. They were about levels, and there's some embeddability results, but I mean, one of the core principles is that any Henselian valued fields with an ordering is elementarily equivalent in this now expanded language to the corresponding power series field with that value group and that residue field. Okay, so that was the short introduction of the model theory and the valuation theory. So let's restate the question, knowing the motivation in the background. The question now is the language LOR more expressive than the language LR in the context of ordered fields and convex valuations? And let's see what that means. So the definable sets we're looking for are the valuation rings. So whenever I say valuation is definable, I mean that the valuation ring is a definable subset of the field in the two languages I consider. And now knowing this, we have two main questions. And that was kind of the starting point in 2018. So the first question is there an ordered field K and a Henselian valuation V on K such that V is definable in the richer language of ordered rings, but not in the poorer language of rings? And the second question, I mean, I just replaced Henselian by convex, is the same for convex valuations. Okay? And I mean, this is not a thriller, so I'll give you the answers right now. So the answer for the first question is no. So whenever I have something Henselian, then LOR and LR definability are the same, they are equivalent. But in the convex setting, the answer is yes. So in the convex setting, we have valuations which are definable in the language of ordered rings, but not definable in the language of rings. Okay? And also to give some credit to some results which had already been known, and I'm sure that I will not quote all of them, so already apologies if somebody here is in the room who's not quoted and cited. But I mean, I guess most things started with Axe's theorem, which is just one page long, but many details are missing, where Axe showed that V min is 0 LR definable in the formal Laurent series field over any given field. And the context where that came from, and often it is quoted as a motivation for the study of definable valuations, was decidability theory. So since we have definability of the valuation, this implies that if F is undecidable, then so is the formal power series field, the Laurent series field. Then there was this theorem of Hong. I always cite both years because one is the thesis and one is the condensed paper, and it's hard to track back which one appeared in the paper and which one in the thesis, so I just always give both references. And kind of based on the ideas of Axe, he said himself, he showed that if you have a Henselian valued field and one of the following condition holds, then we get LR definability with one parameter. So it's not exactly what he proved something stronger, but this is for our context the kind of core that we are using. And the two conditions that are sufficient is either VF is discretely ordered meaning there's the least positive element in that group, or VF is densely ordered and contains a convex subgroup that is P regular but not P divisible for some prime P. Okay, so this is a long condition. I do not want to go much further into this because I will present later a generalization of that, which is much more accessible in the context of a 60-minute talk. But P regular just means, I guess, taking the quotient with any proper non-trivial convex subgroup gives you then a P divisible group. Okay, and I also want to refer to the work that I always used for reference. There was this survey of Arno Fehm and Franziska Janke from 2017 where they really collected many more definability results for Henselian valuations. Okay, but since I came from convex valuations and not from Henselian ones, there was another result which kind of was my personal starting point. So it was from the work of Franziska Janke, Pierre Simon, and Eric Walsberg from 2017. It was actually in the context of the study of DP minimal ordered fields. And there they showed this result that if the ordered field K is not dense in its real closure, and when I talk about these topological notions, I always mean with respect to the order topology, but I'll make some sketches later also. So if K is not dense in its real closure, then K admits a non-trivial, LOR definable convex valuation. So the existence of an LOR definable non-trivial convex valuation is already insured as long as the field is not dense in its real closure. I mean, the kind of the worst thing that can happen is that the field is real closed itself and then no convex non-trivial valuation is definable because of O minimality. But I also come to that later. Okay, so let's get started with Henselian valuations. And let's get one thing out of the way, the answer to the first question. So we proved in this paper that if we have a Henselian valuation on an ordered field K, and this valuation is already definable in the language of ordered rings, then it is definable in the language of rings. Okay, so pretty much most of the paper is dedicated to this proof, and the proof itself, even with the lemmas we prove on the way there, is quite long and technical. But I want to just mention one very crucial component of this proof, and that is that the value group and that's very important, ordered residue field are stably embedded in the upstairs field, in the big field. Okay, so what is new? I mean, this is all known for the context of rings in the language of valued fields, not of ordered valued fields. And what we proved is that also with the ordering we have stable embeddedness, stable embeddability. And what we do very often, I mean, just to give you an idea of how stable embeddability helps here. I mean, stable embeddability means we can always kind of switch between the upstairs field, the value group, and the residue field. And many times we have something like, a definable valuation is lurking somewhere downstairs in, let's say, the residue field. And we somehow want to compare valuations. And the good thing about stable embeddedness is once something is definable upstairs, it's also definable downstairs. And when I say it, I mean the induced sets on the value group and the residue field are definable also there. And so we always kind of go up, down, up, down. I mean, going up is, for that you don't need stable embeddability, but the going down argument appears quite often when you look at the proofs. Okay, so I said I want to get this out of the way because this result tells us that for this section of the talk, we can really restrict ourselves to LR definability. And that's also why I now switch to the context of general fields. Okay, I mean, I'm still interested in the ordered context, but why not do it for any field if we can? So also to give you something which might be interesting, I mean, the concept of parameter-free definability will come up later. So we really showed this result for definability with parameters. One interesting question may be whether this still holds for parameter-free definability. Probably many of the concepts from our proof can be applied, but I mean, it's always this thing, you have to keep track of the parameters you use, and the proof would have become much, much longer, and I guess also in the stable embeddedness part you would need a bit more because the quantifier-free definability also depends on the parameters. I mean, you really have to keep track that you have some version here where parameter-free definability also somehow goes downstairs, as I just said. But yeah, this is something that might be interesting. Okay, so now to another paper. So since we now know LR and LOR definability are the same in the context of Henselian fields, let's look at some sufficient conditions for LR definability of Henselian valuations. And this is now in the spirit of Ax and Hong, and I'm giving the result of Jochen Königsmann also later. So we proved that if we have a Henselian valued field, then independent of the residue field, we only have to look at the value group. If the value group is not closed in its divisible hull, then the corresponding Henselian valuation is definable in the language of rings with one parameter from F. Okay, so we have definability with exactly one parameter. And being not closed in the divisible hull came up as a kind of strange condition. But these topological conditions reappear all the time. So the divisible hull, I just wrote it down here, is the smallest group containing G, which is divisible. So where every element can be divided by any natural. And to me, the divisible hull was always kind of the analog in the context of ordered abelian groups to the real closure in the context of ordered fields, because it's kind of the smallest O minimal superstructure of the same kind containing it. And these things reappear, and I mean, this is no coincidence. So really many of these proofs rely on the fact that we kind of have here definable closures in some O minimal context. So this is what we use all the time, and then these topological conditions are something which we can also express in languages. So being closed in the divisible hull, or being not closed in the, well, I stated positively, being closed in the divisible hull means it contains all its limit points. And somehow you can express that in the languages that we're using. But what I want to point out here is that this is a strict generalization of Hong's result. Just for comparison, I highlighted here the conclusion is the same, the setup is the same. The condition on the value group is different. So Hong said that it has to be, I artificially added densely ordered so that we are in the dense context. But Hong said that we need a convex subgroup that is P regular but not P divisible for some prime P. And we actually showed that this here is more general by also presenting a group that satisfies our condition up here, but not the condition down here by Hong. Okay, so that is now kind of, to our knowledge, the strongest known general definability result that only depends on the value group for the Henselian case. Okay, so the value group being not closed in its divisible hull is currently the strongest, for me at least, known result where we always get LR definability. So to give you some examples of these groups, because I think they are not too intuitive if you have not studied, ordered abelian groups that much. One easy observation, any discretely ordered abelian group is closed in its divisible hull. So Z is closed because obviously any limit point of Z in Q is already in Z. Okay, so just a simple observation. But there are more interesting examples. So let's look at a non-divisible group G and a divisible group H. And I always write the lexicographic sum like that. So it's just the direct sum of two groups and then ordered lexicographically. Then G plus H is densely ordered. So the being densely ordered really only depends on the second component. And is closed in its divisible hull. Okay, so there's this example. Z plus Q would be one example. This one is closed in its divisible hull. I try to draw a picture. Mariana had in her talk similar pictures. So we have the first component Z, and for each integer, and I just do these three, we kind of have a copy of Q sitting there. So these are kind of copies of Q. And then when you want to compare two elements, so for example this one and that one, then this one is bigger than that one because I reached this one by going right, and that is already enough, and then going up. But also this element up here is bigger than the element down here. So this is how I would imagine that. And here, of course, we have on each of these arms, we have a dense ordering. And if you think about it, then you can see that it's closed in its divisible hull, because what are the missing points in the divisible hull? So the divisible hull would be Q plus Q, ordered, blue is maybe not a good color, I do red. So the gaps are these arms in between. These are the missing ones. So the divisible hull has all of these arms. But when we talk about limit points, then we really only stay on one of these arms. So when I want to look at a limit point in here of this set, of this group of Z plus Q, so when I look at the limit point of that one, I need to find something that, I don't know how to explain it. So, for example, these can't be limit points. This is what I want to say. So any element on here is bounded away by just taking any interval on that arm. So this element here would be bounded away from that group. Okay, so this is how you show that something is closed. Okay, there's more examples, but the idea is always the same. So we can take something like an infinite Hahn sum. And this is either divisible, meaning that each component is divisible, or it's closed in its divisible hull. Okay, that's also something we proved in the 2021 paper with Salma Kuhlmann and Gabriel Lurici. So you can make up lots of these examples by just taking order to be in groups and taking lexicographic ordering, the lexicographic ordering on direct sums of these. Okay, one further interesting example, which was kind of the leading example for most proofs we did in that paper where we generalized Hong's result. So let's look at something that is non-divisible but densely ordered. For example, the 2-divisible hull of Z. So make everything 2-divisible, but there are still elements in there which are not 3-divisible. And I mean, I just give them all to you now. It's quite interesting. Depending on how you combine A and Q, you get groups which have completely different properties with respect to being sitting inside the divisible hull topologically. So if you have Q plus A, then it's dense in its divisible hull. If you have A plus Q, it's closed in its divisible hull. And A plus A is neither dense nor closed in its divisible hull. I mean, I would have a lot of fun drawing all these pictures and showing these elements, but these are also quite nice exercises or illustrations of how you can find, just from these very tiny blocks, these nice group examples of groups somehow sitting topologically in their divisible hulls. Okay, so now here's the promised result. That was all the case where we had order to be in groups of arbitrary rank. So here is kind of the rank 1 case. The rank 1 case up to elementary equivalence, I would say. So there's this result where I couldn't really track where it comes from, but Hong proved it and then said that there was a remark that Jochen Königsmann proved it earlier, but also Ax had a version of that, but then you have to apply some transfer principle by Ax, Koch, and Ershoff. Anyway, so kind of the result that goes back to all these sources and possibly more is that if you have a Henselian valued field, then we already have 0 LR definability, so parameter-free definability, if either the value group is discretely ordered and elementarily equivalent to Z group, or it's densely ordered. I mean, I just added that so that you have the distinction. So densely ordered follows actually from here. So it's densely ordered, non-divisible, and dense in its divisible hull. And that is actually equivalent to saying that VF, that group, is elementarily equivalent to a rank 1 group, to an Archimedean group, which is densely ordered. So these are the so-called regular groups. And in these cases, the valuation, I just said it, is 0 definable. I mean, the arguments, or some arguments, are quite nice. Since these are rank 1, there are no how does it go? No coarsenings. So once you have a rank 1 valuation, then there are no non-trivial coarsenings of that valuation. And this is somehow how you get that you can really identify among all the definable valuations by a certain formula the ones with rank 1, and that lets you eliminate the parameter. That is one way to go about it. Okay, so combining the results that we have, and now I really put them right next to each other because I want to make a point towards parameter-free definability. So let's compare the conditions. So in now the Hong plus our results, we have that VF can be discretely ordered, and in the dense result, we have VF being not closed in its divisible hull. And then we have still one parameter. So you can very easily see that anything that satisfies one of these two conditions satisfies one of these two conditions. So these are weaker conditions, strictly weaker conditions. And the question that we asked ourselves was, can we show that in general we cannot reduce to parameter-free definability? And that's what we did. So, I mean, it's kind of, yeah, I mean, you really have to look at it. So we have discretely ordered here, and then we have definability. And if on top of that it's a Z group, then we have parameter-free definability, and something similar in the densely ordered context. And what we did was to prove the following theorem. So in order to give a counterexample, that's always a good thing. We just have to find one example. And there's different ways to go about this and to do this, but the one that we chose was the following. We showed that for any ordered abelian group which is non-trivial, there is a Henselian valued field K, and I now say really K because we also made it ordered, such that the value group is this infinite lexicographic sum, but I mean infinite to the left. That is important here because we'll soon see two examples where this ordering is important, and also for the proof, we really have to go to the left in constructing this value group. And K admits no non-trivial, zero LOR definable Henselian valuation. So it's almost an overkill. It's enough to show that actually V is not zero LOR definable. So here is a non-definability result. So we have a specific example, and we can find for a strange value group that looks like that an ordered Henselian valued field such that the corresponding valuation is not zero LOR definable. And the construction method of such a field relies on the construction of a T-Henselian, non-Henselian ordered field with taking care that the value groups are the ones that we want them to be. So T-Henselian means, so a T-Henselian field is a field, in our context, is a field that is elementarily equivalent to another field that has a Henselian valuation, but a T-Henselian field doesn't have to have a Henselian valuation itself. Okay, and so being T-Henselian and non-Henselian, so being T-Henselian but having itself no Henselian valuation, which is non-trivial, means that it cannot have, or anything elementarily equivalent to it, cannot have a zero definable Henselian valuation. So that's also a standard procedure, not invented by us, where you can show that something is not zero definable. Okay, and now for comparison, the groups that we chose in order to relate this result, or in order to show that here we really can't get rid of that one remaining parameter, are the following two. So if you choose Z, so you have Z plus Z plus Z and so on plus Z, then you have a discretely ordered abelian group. Because I said it earlier, being densely or discretely ordered really only depends on the last component. And if the last component is discretely ordered, then the least positive element in here will be also the least positive element of the whole group when we set just every other component equal to 0. Okay, so with that it's easy. What about the other case? We need a densely ordered and not closed in its divisible hull ordered abelian group, and there we take the two divisible hull of Z again. And that will do. That is densely ordered because then the last component will be densely ordered. And it is not closed in its divisible hull because I said so earlier. So I said earlier this here, but I mean the same argument applies if you have infinitely many copies of A. Okay, so this is what we've done for the Henselian valued field context. Okay, looking at the time, I should continue. So what about convex valuations? So when you talk about convex valuations, you lose a lot of the machinery and also of the known results in the literature, because, at least to my knowledge, that 2017 result by Franziska, Pierre, and Eric was the only one I knew where really somebody pinpointed down definability of convex valuations in the language of ordered rings. I didn't know it, or I still don't know any other results in this context. So let me mention it again. The result was that if an ordered field is not dense in its real closure, then it admits a non-trivial LOR definable convex valuation. So that's an existential statement. So we are always about having a certain valuation and finding out whether it's definable or not, but this is an existential statement, so there always is one. So the question is, or this is kind of where, for me at least, this started, when is K not dense in its real closure? And there's this result, it's easy to prove, that if K is dense in its real closure, then for any convex valuation V, the residue field is really closed and the value group is divisible. I mean, it's really a standard result. And that already tells us that if you have a non-trivial convex valuation such that either the residue field is not real closed or the value group is not divisible, then we are up here. And that happens in, I would say, many cases. I mean, yeah, there's no quantification of how many fields there are and how many are dense in its real closure, but I would say just it's more naturally for a field to be either real closed or not dense in its real closure than for a field to be dense in its real closure. Some people might disagree. Okay, so let's look at cases where one of these two is satisfied, but we need to make it more specific, because if one of these two is not satisfied, we just get the existence of a definable valuation. But what we want is, give me a valuation, I tell you it's definable. So our result here was that if we take a convex valuation on K, and at least one of the following is satisfied. The value group is discretely ordered. This theme reappears. The value group is not closed in its divisible hull. We also saw that before. Or the residue field, and that is now new, is not closed in its real closure. It's a bit, to me, it was always a bit strange because I always got mixed up. Here we need something being not dense in its real closure, and here we want something to be not closed in its real closure. But really here we are in the residue field. Okay, and then the valuation is LOR definable. And in the first two cases, even with only one parameter at most. In the last one, you need more because you need to talk about elements which are in the real closure, and there you need polynomials which might depend on more than one parameter. Okay, so just for comparison, the group case really is exactly the same as in the Henselian context. And that is also kind of a recurring theme, that somehow convex valuations inherit some of the nice properties of Henselian valuations. Although it's a bigger class, still sometimes these conditions reappear which also give you definability, but in this case really only in the language of ordered rings, and the proof methods are completely different, I would say. I mean, yeah, just because of the presence of an ordering, we kind of have to be more along the lines of here, where you really construct convex sets using the orderings. Okay, and also to give you a glimpse at parameter-free definability, we have pretty much the same, because the same principles I mentioned earlier still apply. If there's a valuation, and that valuation has some property which I can express in the given language, and this property makes it unique, then I can kind of get rid of the parameters by kind of saying, well, I mean, these are the standard tricks. I introduce quantifiers. I mean, that would be one trick. I introduce quantifiers, and then the parameters disappear, but I quantify over variables which I plug in, and then I say something about it. So I say that these are the parameters that define the course's valuation doing something or something like that. So that is kind of the idea, to get rid of the parameters. And the conditions here are also the ones you've seen before, except the third one. I'll talk more about that in a second. So the first two conditions are discretely ordered and elementarily equivalent to Z group. And the second one is densely ordered, non-divisible, and dense in its divisible hull, as before. So we still get kind of the analogy to the Henselian case. The third one is being not real closed, but dense in the real closure. Yeah, exactly. Being not real closed, but dense in its real closure. Yeah, there you go the other way. So once you kind of have a valuation on KV, then suddenly what you get is a real closed residue field. So if you are dense in the real closure, I said it earlier, and you would have another valuation on KV, which would correspond to a finer valuation on K, then the residue field of that finer valuation would be real closed, and there we have it. So kind of we can get rid of the parameter by saying, well, it's the maximal step you can do before the residue field gets real closed, and you can somehow also express that in the language. Okay, just a few examples. Every Archimedean field is dense in its real closure, okay? But more importantly, density in the real closure transfers via LOR elementary equivalence. It's not too difficult to prove that, but there are also some very nice proofs which go back to possibly McKenna in the 1970s, possibly. And there's also some nice, let's say, axiomatizations or some theories which imply density in the real closure. So these fields have actually also been studied. Okay, another example. the ordered field of generalized power series is either real closed, and we know when that happens, if the residue field is real closed and the value group is divisible, or it is closed in its real closure. And that is also, again, a reappearing phenomenon. When you have these Hahn constructions, these lexicographic sums, then in the ordered topology, you become closed very, very quickly. So the cases where we have neither dense nor closed, they are the rare ones if you just look at the fields we look at. But I want to give you an example. So just take Q and add one infinitesimally small positive element T. Then this is neither dense nor closed in its real closure. And since this is quite a nice example, I would say. So for example, the square root of 1 plus t squared, you can use the Taylor expansion of that, and that is not inside Qt, but it is a limit point. So inside its real closure. Okay, so we have a limit point which is not in Qt already. What else do we need? We need something that is not a limit point. So not a limit point would be square root of t. It's not a limit point. For example, I could look at the interval square root of t minus t squared, square root of t plus t squared, and this interval so contains square root of t, and it bounds square root of t away from Qt. So no element of Qt lies inside here. That's another way to go about it algebraically. I mean, I could also do a sketch, but what happened here is kind of we are now on an arm which doesn't exist in Qt, and therefore it's completely bounded away. That's the sketch I made earlier. Okay, so we have a field which is neither dense nor closed in its real closure, because we have the existence of limit points and the existence of non-limit points. Okay, so now answering our second main question, which was the same as the first main question, only for convex instead of henselian valuations. There's this very nice lemma, and here's the field from the beginning. I take Q and add countably many transcendental elements. And what we proved in this lemma, and again, I think this is a highlight. I mean, often it's the small results which are, at least for me personally, the highlights. This is a non-definability result for valuations. And so the statement says that if we have this purely transcendental extension of Q, and we have a valuation on this field where the first element has negative valuation and all the others lie inside the valuation ring. I mean, it's not necessary that's exactly this configuration, but I mean, just makes the proof easy and also the application. The most important thing is that the valuations of one element is fundamentally different from the valuations of the other. Then V is not LR definable. And again, that's a reappearing theme. I proved exactly that in a different context earlier. So we can kind of find an automorphism on Q, which switches the places of all the SI, which fixes the places of all the SI except maybe two of them. I mean, the proof goes a bit differently. We have to find another transcendental element, but that's pretty much the proof. So you find LR automorphisms by mapping transcendental elements to other transcendental elements, and then you get non-definability. So this is really, second week of a model theory class, principles applied in order to get a non-definability result. And so here's the example of a valuation which is convex, which is even 0 LOR definable. So if we can do it, why not do it properly and get the strongest case, but not LR definable even if we take parameters. So we take as the residue field a purely algebraic extension of Q, where we just take an arbitrary set of algebraically independent elements inside the reals. Okay, so do not get confused. This whole thing is now our residue field. Missing is still S0. So S0 comes into play now. Our S0 is t to the minus 1. So we adjoin to K this element t, which is just a formal variable, saying that it sits inside the formal Laurent series field. Okay, so this is an ordered field by the ordering I introduced earlier. The residue field has the ordering inherited from R, and therefore we get that ordering that we can carry upstairs in the Laurent series field. So the value group of that is just Z with respect to the valuation from the Laurent series field. Well, I mean, obviously because really we just added elements whose powers are multiples of 1. And that shows that V min is 0 LOR definable. Because if the value group is a Z group, then the valuation is parameter-free LOR definable. That's the result I showed earlier. However, let's look at that one element as 0, which has negative valuation, and all the others are in the residue field, so they have 0 valuation, and that is what we need in order that V min is not LR definable. So it's a very, very, I find, nice example that doesn't rely on much. I mean, if you really just go into this proof here and this proof here, it doesn't rely on much, but gluing it all together and together with this wonderful lemma, I think makes a very nice example. Okay, so I hoped a bit that I wouldn't reach that point, but I have another 7 minutes to talk about the topic I know least about. So I'll give my best. Okay, so almost really closed fields. That is kind of now, we are kind of changing the topic a bit, but we're still within definable valuations. So almost really closed fields, I mean, we've heard about, nice talk about also almost mathematics. There's also these almost really closed fields introduced by Definable, but also some other people at kind of the same time. Since we are in this community, we use really these results about almost really closed fields, which they are called. And I say that a field doesn't necessarily have to be ordered, but we'll see in a second that it will be. Is called almost really closed with respect to a valuation V. I need to introduce that to talk about it later. If the valuation is Henselian and the residue field is real closed. Okay, I mean, here real closed really being in the language of rings, real closed. But, yeah, I mean, I already give you all the 4 points. So a few things to notice. Well, I mean, there's always one nice representative, just model theoretically, in LR elementary equivalence, even also in LOR elementary equivalence of any almost really closed field, and it's just the power series field over R, and G can be any ordered abelian group. So that is then the value group. So by Ax-Koshen-Erschow, kind of any almost really closed field is elementarily equivalent to a field like that. Okay, any almost really closed field can be ordered, but the ordering doesn't have to be unique. The amazing result here, the converse of Knebusch-Wright holds. So any convex valuation is already Henselian. And to me, that was kind of the incentive to also look more closely at these fields, because this happening must mean something. And definable Henselian valuations were really, really nicely studied in the paper where also these almost real closed fields were introduced by Definable. And the results that are there for this particular class of fields are partly stronger. So for this particular class of almost really closed fields, the results even generalize the results that we have. So mostly here conditions on the value groups are given in order to obtain definability of Henselian valuations. And what we proved was that in any almost really closed field, for any ordering, any LOR definable valuation, a lot of for all quantification here, so any LOR definable valuation doesn't have to be convex. So any LOR definable valuation is already, okay, I cheated here, is already Henselian, therefore also convex, and therefore already LR definable. So we started with LOR definable without any further conditions, but we proved that the valuation is Henselian. And since this valuation is Henselian, combining it with the other result, it's already LR definable. It's not exactly the argument we used in the paper, but for this talk, that's the important information. Okay, so almost really closed fields are extremely nicely behaved. Okay, so classification of strongly dependent ordered fields. Almost really closed fields are quite interesting in this program, which also was one of the main motivations of this whole conference, the classification of NIP fields. And in the ordered context and also in the context of strong dependence, but I mean, probably all things should, I mean, it's conjectured that all things also already hold in the NIP context. The question is what are necessary and sufficient conditions on an ordered field to be strongly dependent. So are really specialized to ordered fields, which kind of is again cheating because all these very difficult cases, or many of them, happen in characteristic greater than 0 case, for example. So we're really here in a very nice setting when we want to study them. And just to give you also my motivation to study these, well, NIP fields, I came from study of O-minimality, O-minimal expansions of ordered fields. And there's this really nice chain of implications. And O-minimality in particular implies strong dependence. So this is a bigger class of ordered fields than the class of O-minimal fields, which is, I mean, kind of completely known. And there's this conjecture which goes back to Szilard, but there have been many reformulations. But what people ended up with is that any infinite strongly dependent field, and strongly you can put in brackets if you want to, is either algebraically closed, some people say separately closed, I'm never sure which of these is the current state of the art, real closed or admits a non-trivial LR definable Henselian valuation. Okay, so that's the famous conjecture. And specialized to ordered fields, we have the conjecture that any strongly dependent ordered field is either real closed or admits a non-trivial LR definable Henselian valuation. Okay, so that is kind of the conjecture if you really look at this setting of ordered fields. And maybe to finish with, just project this whole slide. What we showed in this paper we started with in 2021 is that this specialized conjecture about strongly dependent ordered fields is equivalent to the following. Any strongly dependent ordered field is almost real closed. And the nice thing is it fits into one line. So any strongly dependent ordered field is almost real closed. So this connects it. I mean, the proof is beautiful. I mean, I don't have time to go much into that, but again, it just applies all these, let's say, high-level concepts that everybody knows, and then you suddenly get this equivalence, plus some machinery that has been developed before. And yeah, maybe I should not go into detail for the other results. I just want to advertise something else. There's a poster session this afternoon, and definability of rings is kind of the topic that the overall topic I was talking about. But in the context of NIP and also IP ordered fields, some other questions have come up. I do not want to go through them in detail because they are also on the posters down there, but these questions of definability, they have a broader context, and the machinery applied is very similar also in these contexts. So I really want to refer you to Laura Würz and Lasse Vogel's posters this afternoon, and then you can talk to them about it. Well, thank you very much.
Are there any questions for Sebastian?
Can you give an example where you really need a parameter to get a valuation?
Yes. Wait a second. Sorry. Where are we? There we are. So it's that one. Yeah. So these are the examples where you really need to have a parameter.
So, but how can you prove that you really need a parameter?
Oh, I see. So we prove it by taking exactly the field we construct here. This field has no 0 LOR definable Henselian valuations, but it has this value group, and the other result tells us because of this value group, it has a parametrically definable Henselian valuation. That's how you prove that you can't reduce the parameter.
Essentially, the field is very snippy.
Oh, you understand that? Okay.
I also have a question. At some point you said you detect, you take the, I don't know, we call them finest crosses so that the residue field is not real close. How do you detect this definably?
So what was the
How do
last?
you detect this definably?
Well, you don't say this is the smallest field such that something is not real closed, but everything smaller is real closed.
How do you detect the latter one?
There you take a particular sentence which is not true in the non-real closed field, but true in the real closed field. And then you somehow say everything that is smaller must satisfy that one sentence, but everything before does not satisfy that sentence. Maybe, that's kind of the spirit of it. So but you have to really be careful because it's not, what I said earlier was maybe not accurate. You can't really say it's the smallest one that has this condition, but you have to say something like every smaller one does not have a certain condition, and that works definably, and the other way does not work definably. But you're completely right there. It's a subtle point.
Are there any other questions?
Quite early on, you gave this example of a field where you don't have, with an ordering which is not definable in LR, with this Q with these infinitely many TIs added.
Yeah.
And I was wondering if you just take Q with one T added and you take any Archimedean ordering, can it ever be definable? So take,
Where was it? Yeah. I don't know, sorry. That's something I thought about it but not for long enough. Probably the ordering should still not be definable, but I don't know why. I do not have a quick argument. If anybody else has a quick argument.
Just by counting, there are uncountably many orderings, and only countably many of them can be definable, but my guess would be that all the Archimedean ones are not definable, but...
Yeah, that would be maybe a quick argument.
Wouldn't QT define a bunch of... So Q defines every computable thing, right?
Mm-hmm.
QT also have that property?
In Qt, I guess Z is definable. Oh, well.
You said that QT, every computable set is definable? Yes. So then a bunch of Archimedean orders.
Okay, there you have your argument.
The opposite, a bunch of Archimedean ones. R? Yeah, R. All the computable ones are definable.
So this strange animal, this field that is not Henselian but T-Henselian, and which is, so to say, product to the left, extending to the left. Is that this field that where for every coarsening the residue field is Henselian, but the field is not Henselian?
For every coarsening, the residue field is Henselian. No, I think not. I think even for every coarsening, the residue field might not be. I'm not 100% sure. I would have to think. You can start with the real. Okay, of course, yeah. You can start with having the starting residue field the real numbers, and then if you.
Because the real numbers are Henselian but not Henselian, right?
Yeah. Okay.
Are there any more questions? If not, we should thank Sebastian again.